Glad to be here. I'm going to be summarizing some of the numerical aspects that we've encountered of this grand challenge, which is the simulation in multi-D of supernova explosions, particularly the core collapse explosions. Given the time allotted, I'm really not going to go into the science here. If people have questions, I'm happy to answer them, and people can interrupt, of course. But during the question period, I might be able to fill in some gaps. But again, I'm going to be talking about our attempts in the context of a large international effort at simulating with some fidelity the physics that is at the interface between nuclear physics, particle physics, statistical mechanics, gravitational physics, and the computational arts, which is supernova theory. Now, the complications are generally because, as is observed, and these are a data set, the debris from a supernova is ejected aspherically. It's not ejected spherically, but it's in tendrils and fingers and blobs and bubbles. And so that means that we have to do these simulations to understand what's happening in full 3D. That's 3D is space, 1 dimension of time, and 3 dimensions of momentum space, because we have to do radiation, magnetohydrodynamics. Now, I'm not going to talk about the magnetic side of this, and I'm not going to be doing it in the 7 dimensions I just quoted. I'm going to be talking about dumbing it down a little bit, as the entire community has had to do, and the development of various techniques, at least in our group, to address this computational challenge. These are data as well. The blue is the distribution of titanium-44 seen with the NuSTAR satellite, and this is just to emphasize that what's coming out is basically coming out in multiple bubbles, and we have to be able to address that. Simulations frequently do give bubble structures. This is in the first second or so in a very simplified simulation with good hydro but bad transport of the emerging bubbles. So we naturally do see these sorts of things, and buoyancy plays a significant role. But the radiation hydrodynamics of this problem is quite challenging. This is another example of it looks like a data. I would like to believe it could be similar to data, but this is actually the shock wave moving out from the protoneutron star and the turbulent inner regions. And we want to be able to do this with the computational fidelity that is consistent with nature, and that's going to be a long-term task. This problem has been around for 50 years, and it's only slowly yielding to solution. That's just a position of the shock wave where it shows just these bubbles that are hitting the surface and these particular types of calculation and the explosion that generally finds its own direction, but again has to be done in 3D. If I can advance this, hopefully. So the mechanisms of explosion, I am going to go over a little science that people have talked about that we have to simulate, have a whole pedigree. There's the direct hydrodynamic mechanism, which again, the core of a massive star collapses in about a second. It's about the mass 50% again of the mass of the sun, collapses, as I say, in a second, achieves velocities about the quarter of the speed of light. It achieves nuclear densities, it rebounds, a shock wave is formed, but that shock stalls in all simulations in spherical symmetry. And this direct hydrodynamic mechanism, where that early shock is the supernova, is aborted. The standard mechanism, which most of the community believes, and I think has great credibility, is that after that stall, then the neutrino heating behind the shock re-energizes the shock. It doesn't seem to happen even in 1D with the neutrino heating. It seems to require the turbulence, and we're going to hear more about that in two subsequent talks, behind the shock in order to actually reach the conditions for explosion. But you can have rotation and magnetic fields. There are a number of things. But basically, the 3D convection-driven, neutrino-driven mechanism is the one that people are focusing on. And that's the one that we're trying to design code for. Important ingredients are the progenitor models, the actual structures in the interior. And we don't have many real constraints on these. You have to do the multi-D hydrodynamics, the multi-D transport, as I say, which is the most challenging aspect. There are many instabilities, and neutrino processes are very important because the transport is not of photons that are relevant in the interior here, but it's the neutrinos. General relativity probably plays an important role. What I'm going to show you are attempts that don't include general relativity. You'll hear a little bit more about that later in Christian's talk. Okay. One of the complications, though, is that there are a variety of groups around the world that are trying very hard to simulate these phenomena that are coming up with results that are not mutually consistent. And so this is one group that is getting explosions, but they're all exploding at around 100 or so milliseconds, depending on the dimension. These are 2D simulations. This is 1D and this is 2D. They get explosions. But another group, which ostensibly is doing similar simulations, never gets explosions at that early phase, but sometimes gets explosions at later times, much, much later and delayed. And so we're seeing a variety of perhaps dependencies on resolution, on input physics, on the accuracy of the numerical schemes for the hydrodynamics and the radiative transfer, et cetera. And we need to get on the same page. One of the themes that's going to emerge from my talk and what I want to communicate is that the community needs to get together to make comparisons for verification studies. And it hasn't yet done that to the degree that's necessary. One thing that is interesting is that when you get to higher dimensions, of course, you dumb down the resolution perforce because of the computational complexity. But when you increase the resolution for these higher dimensional simulations, the explosions are less prominent, less likely, it seems. Higher resolution actually can turn an exploding model into a non-exploding model. And so this is an issue. Resolution is important. This is just the results of another group. And in 2D and 3D comparisons, this particular set of calculations sometimes led to 3D explosions, but not 2D explosions, although recently they've tweaked some of the microphysics and they say they can get some weak explosions. When we do these simulations in 2D, we get 1D here, where this is the shock position, 2D shock position. What an explosion is this is going out to infinity. And we're not getting explosions with ostensibly similar physics, although these calculations are not including even a fake attempt at general relativity. And that might be an interesting aspect. So problems, though, that I'll summarize with the exit models is that many of those that are getting explosions, not all, though, although sometimes they have other problems, are using the so-called ray-by-ray approach, which is actually not doing the transport in multi-D, but doing multiple 1D calculations. The ray-by-ray is not actually following the rays of radiation. It's just going along the radial rays in the grid. I think that there are errors, at least at any particular time in any particular direction, in the neutrino matter couplings that could be as much as 10 to 50%. Many of these explosions are under-energetic, particularly when you go out to large distances and include the ejection of the outer core. Many of them excise the inner cores because there's a Courant problem as in the spherical converging models that insensibly to avoid that, they frequently excise the cores. We never do that, but we sometimes pay a penalty. The low spatial resolution is an issue, as I say. Relativistic transport has really not been executed with any great, in any great detail. Multi-angle calculations are very rare. There's only been one in multi-D space that has been done, as by our group, it's Christian. There are different results. The progenitors, of course, are crucial, and different modelers who know the nuclear physics are providing us with initial conditions that are very different. And so that's a real problem. So one of the things I'm going to emphasize is 2D and 3D. I'm going to go through a list of problems. 2D and 3D are very different. This is a nice demonstration of that by Sean Couch. A 2D simulation looks like this. It's a Raoul. And 3D simulation, corresponding 3D simulation, looks like this. I think you can tell the difference. When we do 2D simulation, 3D simulations, we get these types of structures, which are pseudo-spherical and have a lot of small-scale structure. When you do the 2D calculations, you have an axis, and you get these sloshing oscillations, which you see more rarely when you do the 3D simulations. And here's an example of a 3D simulation, again with simple neutrino, very simple neutrino transfer. But you don't get an axis in here, certainly along the computational axis. You get a lot of small-scale structure. And the way this thing was constructed, it's going to explode, but it finds its own direction. A bubble basically leads, an L=1 bubble basically leads the explosion. But you don't get the sloshing action, which you almost always get in the 2D simulation. That is an artifact of the 2D to a great degree. The ray-by-ray I referred to before also tends to exaggerate, could exaggerate certain aspects of the simulations, and you get wild temporal and angular variations that aren't really there. This is an example of the vectors are actually the flux vectors coming out, and the background color is the oscillation of the object in 2D again. Again, don't trust it too much, but you see that wild oscillations in the matter profiles don't translate into wild oscillations in the radiation field, because radiation is an integral quantity over much of the material. And when you do ray by ray, you're looking only along this direction. So I think that is a real problem. And this shows us as well the variations here in angle are the matter variations, and the radiation field is actually much smoother. And this is not captured by many of those simulations that don't do the transport with ray by ray. These are just example numbers of the challenge, the computational challenge. This is not current. This was a little while ago. But look at these sorts of. If you want to do full matrix inversions, you're talking about inverting with global solves using Krylov subspace methods, matrices that could have as many as 200 terabytes of elements or petabyte elements. The operation counts are quite severe, and if you really want to do the full coupling multi-angle, you get to about 10 to 20 operations, floating point operations per second.
Why do you have to invert a matrix?
I'm getting to that. If you want to do global implicit solve, then you have to invert a very large matrix. You're getting to my punchline. Thank you, Bob. And this is a bit of the history where in the past we could do calculations with maybe 1,000 CPU hours, and we had a small memory footprint. What we're going to go to is something like a very large petabyte memory footprint, and the requirement for basically 10 to the 5, how did I put that? It should be 10 to the 9 CPU hours per run. That's with the fully implicit calculations. And because of these numbers, we've stepped back. It turns out, so the various codes we've used have all sorts of interesting features. There's been a lot of numerical effort here. Moving mesh, ALE approaches, multigroup flux limited diffusion, 2-moment closures, being able to include rotation, having magnetic fields in there, et cetera, with this particular approach. Our old Castro code, actually, it was a second order unsplit. It used block structured hierarchical grids, AMR, BoxLab software infrastructure. All these things were necessary, we thought, to approach this problem subcycling time, and the code basically works. But it had to use these multi-grid and Krylov methods in order to actually solve, with preconditioning, actually solve the huge matrices that were necessary when doing the calculations for the transport implicitly. And these are the types of grid structures that we could do with the AMR approach. You see the hydro background, and you see the various AMR levels of refinement in here. I always have trouble with this movie. However, what we realized was, and a number of other people are realizing this as well, is that in the supernova problem, the sound speed is close to the speed of light in the interior, and radiative transfer can actually be done explicitly. Bob? No, it's not so obvious in most cases. If you want to include all the terms, the light travel time across the zone is relevant. But in fact, because of this, our Courant condition is actually basically the most, almost the most stringent condition. So we can go back and actually do these calculations explicitly. And that has given us a speed up which about a factor of 10. And so what we've been spending much of our time on Blue Water's doing is getting a new code going that supersedes our previous code, which is a pretty sophisticated one, but has bottlenecks at around 12,000 cores. This is the wall clock time, and we're not getting improvements beyond that. So the new code, and don't worry about the details, has some of these things. This is in collaboration with Josh Dolence in particular and Aaron Skinner at Princeton. Solves the 2-moment transport equations. It needs a closure. It does the transport. It solves the transport operator with Godunov-like approach, just like hydrodynamics. There's some similar differences. It has the terms to order V over C, so it's velocity-dependent terms. It's implicit in local transport terms, so there's no global solve necessary. Explicit Newtonian hydro. Conserves energy, momentum, and lepton number to machine precision. It's very good with gravity. That's an interesting issue, but that's offline. Multiple gravity. It has a number of bells and whistles, but the major thing is we're getting a factor of 10. And this is a scaling study. I'm almost finished. This is a scaling study. Wall clock time. This is recent in the last couple of weeks because this has been a very strenuous development effort of Fornax, which is our new code's name. Strong scaling in 3D, multi-group, fairly high resolution in space. As we go up in core count from 1,000 to 164,000 integer cores, so it's about half. and it'll go up further than that. And you can see our old code's performance here, and this is the new code's performance. And this is why we waited to get that difference. And so we were originally supported to do 1 or 2 heroic simulations in 3 dimensions using Castro. But what we've been able to do is actually increase the efficiency of our approach to this problem by about a factor of 10. And so we can probably do 5 simulations, whereas before we could do 1.5. It's been well worth the effort. And right now, the only bottlenecks we're encountering are we have to get to good parallel I/O. And so I've been talking with people here about this, and it's been good to network with those people who know how to do these sorts of things. So I wanted to show you this. This is a Castro calculation, and this is towards the end of my talk, which is very high resolution. This is a 2D simulation, and it has this oscillation along here. This calculation took 2.5 weeks of wall clock time. This is the same, slightly different resolution. This was just a test, but it was almost the same resolution of the same model. It's a little speeded up just for the purpose of speeding up. Predict this model, and this took 18 hours. So there are improvements that are possible with these approaches. So the advantages of this new code, and again, we haven't demonstrated with science, we're just on the cusp of being able to simulate these things with this approach, is that it gives us a speed up of about a factor of 10. There are no implicit solves. The Krylov subspace methods and the related things and preconditioners are not necessary. We have static mesh refinement in the interior to get around the Courant problems. The scaling you saw, which is almost perfect, it has linear scaling in energy group number. Implicit codes have quadratic scaling. And it may enable, for this reason, it may enable a whole class of 3-dimensional supernova simulations that will allow us to go to into the future. Thank you very much for your patience.